Hi, good afternoon. Welcome to reInvent. My name is Jeff Lyon. This is Andrew Kiggins. We'd like to talk to you today about defending against DDoS attacks. There's no Q&A for this session, but Andrew and I will be available at the AWS security booth afterwards for any questions that you might have. So we'd like to get started by talking a little bit about the threat landscape and some of the more common attacks that we see on AWS. From there, we're going to move into a discussion of the mitigations that we use to defend AWS infrastructure. And then we're going to talk about architecture that you can employ to take advantage of some of the mitigation that we've built. So some information that's useful going into this presentation is a basic understanding of DDoS attacks, IP-based protocols, and the OSI model. It's also useful to have an understanding of architecting on AWS using services like EC2, VPC, ELB, and edge services like CloudFront and Route 53. And lastly, it's good to have a basic understanding of reading packet captures with Wireshark, because later in the presentation, we're going to take a deep dive into some of the attacks, and we're going to be using PCAPs in that process. So let's focus on some of the common attacks. If you read the news a lot, you see a lot of headlines, and sometimes they can look kind of scary. Headlines like, criminal extortion, DDoS attacks are more powerful. Mega attacks on the rise, DDoS reflection attacks. And then there's this one. If you attended the keynote this morning, you noticed Andy said, the cloud is the new normal. Well, according to this headline, 200 to 400 gigabit DDoS attacks are the new normal. But that's not what we're seeing. While they do occur, we see that the average attack is just over a gigabit. And this is well within our ability to handle within our infrastructure and some of the architectural best practices that we're going to discuss. We also see that the average attack is about 39 minutes. That's interesting because that's long enough for an attacker to cause an impact to your application, but not necessarily long enough for you to be engaged, do a root cause analysis, and then drive resolution of any impact to your availability. And lastly, we see that 85% of attacks are directly targeting the network or the service infrastructure. And for that reason, we want to focus in those areas with a lot of the mitigations that we've built. So despite all of the different reflection attacks and different vectors you hear about in the media, we'd like to focus on DDoS attacks in terms of three basic categories. First, volumetric attacks, or layer 3 attacks. These are attacks that attempt to impact the availability of an application by congesting the network with more traffic than it's able to handle. Similarly, there's state exhaustion attacks. These attacks can also be large in volume, but are more targeted towards abusing the protocol and stressing the ability of servers, IPSs, firewalls, and load balancers to prevent them from being able to handle new connections. And less frequently, we see application layer DDoS attacks. These are attacks whereby the attacker attempts to emulate real user traffic and exhaust resources of the application. So I'd like you to take a look at this pie chart. You're going to see it again throughout the presentation because we're using it as a breadcrumb. And what that means, in the upper right-hand side of the screen, you're going to see a green slice or a yellow slice or a blue slice, or a combination of the three. And we're using that to indicate whether an architectural best practice or a mitigation best applies to volumetric attacks, state exhaustion attacks, or application layer attacks. So by and large, the most common attack that we see today is the SSDP reflection attack. These are attacks that can be large in volume, but luckily are also very easy to detect because they have a clear signature. Some other volumetric attacks that we see are NTP reflection attacks, DNS reflection attacks, Chargen attacks, and less frequently SNMP reflection attacks. You'll notice, and you'll want to take note for later discussion, all of these are on the UDP protocol. In terms of state exhaustion, TCP SYN floods have always been pretty common, and we continue to see that they're common to this day. And lastly, application layer attacks. You may be familiar with attacks like HTTP GET floods, slow LoRa's attacks. These attacks remain common, but the new trend that we're seeing is DNS query floods. And this is a little bit different from a DNS reflection attack in that it's not a reflection, it's not a DNS payload, it's actually a legitimate seeming request from an actual user, or appears to be from an actual user. But in fact, they can be malicious in targeting the ability of a DNS server to serve legitimate users. So I want to focus a little bit on volumetric attacks, specifically UDP amplification. These are somewhat easy to launch, and the way that they work is an attacker who wants to impact the availability of a network or an application can spoof the IP address of their victim. Spoofed requests are then sent to what's known as a reflector. A reflector is a regular server on the internet, hosting DNS, SSDP, NTP, and so forth. And these are often unwitting participants in the attack. And what that means is, say that the attacker sends a small request to the reflector will then respond oftentimes with an amplification that's much larger than that initial request. So depending on the amplification attack, or the specific vector, it has what we call an amplification factor. The amplification factor can be 30 times the size of the request, or as large as 556 times the size of the request. And so what that means in basic terms is, if the attacker sends 1 gigabit of traffic, it's possible that these reflectors could unwittingly respond with 30 gigabits of traffic, 500 gigabits of traffic. Luckily, we've not seen that occur yet, but these are possibilities if the attacker finds enough reflectors in order to cause these reflections. And we also see sometimes that DDoS attacks occur with multiple vectors. Sometimes the attacker will send an SSTP flood, an NTP flood, a DNS flood. But sometimes they'll also do a combination of these attacks. So let's take a look at an example. In this particular example, over a period of time, an attacker first tried an SNMP amplification, was able to generate a little bit of traffic, but not too much. Later, we see some UDP fragments and another SSDP reflection attack. But it wasn't until later that the attacker tried an SSDP reflection attack in conjunction with an NTP reflection attack and was successful in generating a much larger volume of traffic. And the interesting thing is that all of this occurred over the course of 6 hours. And so what that means is, if you were paying attention to your network traffic, you may have noticed the attack initially, SNMP amplification, and had a period of about 5 or 6 hours in order to respond, in order to put your resources on standby, begin scaling your application, or taking other defensive measures. So now let's take a look at the mitigations that we use on AWS. So when you're in your own data center, the infrastructure and the security remains your responsibility. This means, in a DDoS context, that you have some options. You can scale to absorb additional traffic. You can deploy DDoS mitigation hardware. Or you can use a DDoS mitigation service. But when you move to the cloud, we take responsibility for providing a secure, stable, and DDoS-resilient infrastructure. So before there were DDoS mitigation, a DDoS attack had the potential to impact the availability of your application. So then came DDoS mitigation services. With these services, which operate by a variety of different methods, you had the ability to offload your traffic to a third-party network who specialize in DDoS mitigation. These companies could then scrub the traffic and return only clean traffic to your network or application. The challenge here is that that can cause additional latency, and that can also be noticeable in some cases by your users. So at AWS, we wanted to think about how to address the DDoS problem. And the first thing that we did was build services to be resilient by design. So let's take a look at what that means. In the case of Amazon CloudFront or Elastic Load Balancing, for example, we primarily only want TCP traffic. That means that a lot of these reflection attacks, the DNS reflection, the SSDP reflection, NTP reflection, we can just drop those on the floor. CloudFront and Elastic Load Balancing will not accept that traffic, and it will not be carried to your application. With Amazon Route 53, it's slightly different. We need both UDP and TCP traffic. DNS is primarily a UDP service, but we also use TCP in case of failover. So what that means is instead of just arbitrarily dropping one protocol or another, we need to look at the header. If that traffic or those requests are not valid DNS requests, we also want to drop that traffic, and we do not want Route 53 to process that traffic. So when we started building DDoS mitigation systems specifically for Amazon, or specifically for AWS, we thought about this, and we said we don't want to cause any additional latency for our users. We don't want these systems to be noticeable for our users. So we built them to be always in line. And this means that regardless of whether there's a DDoS attack, they're always inspecting traffic and always making decisions as to whether traffic needs to be dropped. We built these on commodity hardware. And the reason that we did that was twofold. One, we wanted to take advantage of advances in commodity hardware, and as that hardware scaled, be able to scale with the growth of the cloud. Additionally, we wanted to be able to quickly iterate on that platform and implement new mitigations when we learned more about the threat environment. A couple other benefits of doing this is it provides us with a low MTTR, or mean time to resolve. And what that means is that when an attack occurs, we can very quickly make a decision to mitigate the attack. And all of this occurs, the inspection or mitigation, in a matter of microseconds, which is not noticeable to users. So what do these systems do exactly? The first thing is a matter of basic hygiene. This means that there's certain types of traffic, bad IP checksums, invalid TCP flag combinations, that we know are not valid. Our customers never expect to receive them, and we want to drop that traffic, and we will. Beyond that, it's not always clear. An elevation in traffic doesn't mean always a DDoS attack. Sometimes an elevation in traffic is a flash crowd or some other form of legitimate traffic. For example, we have customers who may decide that they need to push a software update and need to do it quickly. That can look exactly like a DDoS attack if you're just looking at the traffic. So our first objective is to make sure that we do not impact our customers' legitimate traffic. So what we've done is we've implemented packet prioritization. So for every packet that comes across these systems, we score that packet. In addition, we have an understanding of what is normal on AWS. What does normal traffic look like? And we also know when there's a deviation from the mean. Based on that deviation, we're able to assign a priority. A priority isn't simply traffic is bad, or traffic is good, or traffic should be dropped. Rather, it's a gradient. It's a sliding scale. And what that means is traffic, relatively speaking, is more or less suspicious than the next traffic, and we need to prioritize it accordingly. So if you look at this example, you'll see that some of these bands of traffic we've identified with a user icon. And what that means is we believe that that traffic is most likely legitimate customer traffic, and we do not want to drop that traffic. In the event of a DDoS attack, we're going to give that traffic priority and make sure that that traffic continues to flow. Then you'll see a small amount of traffic running along the bottom of this chart, and you'll see that we labeled it with the DDoS icon. That's low priority traffic. And normally, it sits well below our normal traffic diurnals. The reason that's interesting is, unlike a lot of different DDoS mitigation methods that are available today, we don't need to make an immediate decision to drop traffic just because we think it might be DDoS. Instead, we can wait and make that decision based on whether we feel that there's a threat to our infrastructure. So in this particular example, there's no threat to our infrastructure. We're going to continue serving that traffic. What that does is allows us to avoid false positives and allows us to implement or engage mitigation when we need it the most. So beyond just mitigating DDoS attacks, we want some additional options of what to do with the traffic if it becomes heavier than we expected. Part of this, we have to understand what is the destination of our traffic. For services like EC2, ELB, these have well-defined IP addresses, and it's very easy for us to say, if an attack is against a specific IP, we know that the target was a certain instance. If you've seen the tech media, read the news a lot, you may have noticed IPv4 addresses are in short supply. That means that for a shared service with a global footprint, if we want to make this service available to over 1 million AWS customers, we need a way to conserve IP space, but still be able to identify what is our target. So what we've done is for any CloudFront distribution we'll use in this example, we've assigned a unique set of IP addresses. And based on that unique set of IP addresses, we can identify our targets. So in the case of a DDoS attack, that allows us to identify the distribution and gives us some new options for what to do to mitigate that attack. This same philosophy is extensible to other services, for example, Route 53. So in many cases, when there's an attack and it arrives at a specific edge location, it makes sense just for us to mitigate that attack, and no further action is required. But sometimes, we find it beneficial to isolate the target to a specific location or to multiple specific locations. And when we do that, it often makes sense to vacate that location, meaning that we'll stop serving legitimate traffic from a location that's under DDoS risk. And sometimes the best idea for us is to disperse the traffic. And that makes it so that an individual location handles only a smaller amount of that particular DDoS attack. And it reduces the risk to those non-targeted customers. So now I'd like to pass the presentation to Andrew Kiggins. He's going to talk about some architecture best practices that you can employ on AWS to make use of the mitigations that we've built.
Thanks, Jeff. So out there, we published a white paper last year talking about the best practices that you could use to build resilient applications on top of AWS. And that's great. That's things that you can do. But of course, I want to show you today that we eat our own dog food. The services that we build use the same set of best practices. And I want to couch some of the things that we're going to dig into in terms of that. And we're going to go through the attacks and the volumetric, all the way to the application layer, just as Jeff has talked about. So the first thing we're going to talk about is the volumetric attack. And obviously, that's the largest attacks we see, and it's also the most popular attack. Certain reasons for that. The first thing is that it's cheap. Anyone with a credit card can go and wander about in the dark corners of the internet, find themselves a botnet, and launch an attack. It's really, really simple. The script kiddies do it. You can see some of the kids that play the games do it. It's very, very simple. It doesn't require any sophistication. And to an infrastructure that doesn't have the right measure in place, it can be effective. But I want to show you things that we do and things that you can do to take care of that. And obviously, it's one of the larger attack vectors seen out in the wild. This is a DDoS attack we saw against CloudFront very recently. And there's a couple of interesting things about this. First of all, it's a mixed attack. It uses 2 attack vectors, which is becoming more and more common. And it's in that time frame that Jeff was talking about. And the reason they typically start to use 2 vectors is, if it's just 1 vector, then the signature for that attack sticks out like a sore thumb. And you can identify it very, very quickly. And so what they're trying to do is make it that little bit harder for the mitigators to actually put the mitigations in place and detect the attack. As we'll talk about in a minute, there's reasons that this had no impact. Sodexis is a mechanism that's used to gauge the performance of any CDN. There's a number of large CDNs out there, and this shows us that this particular attack had no effect on CloudFront. Why not? The DNS reflection and the UDP flood are UDP attacks. CloudFront only accepts HTTP traffic. It's over TCP, therefore, it gets dropped. That's really good news if you're a CloudFront user, because as you know, the way CloudFront is charged does not deal with inbound traffic. So not only is it going to take care of your DDoS, it's free. Is there anybody that doesn't like free? Good. I want to dig into the actual attacks themselves a little bit, just to give you a little idea about the signatures. This is a Wireshark. We grabbed a PCAP of the attack. We have a lot of visibility tools internally that we've built that we can dig into the attack. There's often these zero-day attacks, brand new vectors. So we want tools to actually go and grab a capture of that attack. For the older members of the audience, it's Ethereal. You'll remember that. For the young bears, it's Wireshark. And the key point here is that these reflection attacks have a very strong signature that we can use to our advantage. Because it's reflected, it's coming from a real server dealing with real traffic. Therefore, it has to be on a recognized port. Now, for SSDP, that port is 1900, always. So when we see a port 1900 in our IP header, and it's got an HTTP payload, and it's over UDP, we can identify that immediately. So if your application is a web server, or you're relying on Route 53 for your DNS infrastructure, it's simply not going to accept that traffic. This traffic is specifically for point-to-point connections. It's used for discovery. So there's really no reason why you should accept that traffic. Next one I want to talk about is NTP. NTP is slightly different because it's used to synchronize servers. Therefore, you can't simply stop that coming in. Otherwise, your server is going to drift out of synchronization with everyone. So you've got to leave that port open. But it does come on a well-known port, port 123. But the tail in this one is the payload. The payload is what's called mon-get-list. And why is that important? Well, it's not the normal use of NTP. NTP sends a very small packet requesting a timestamp, gets a very small one back. When NTP was developed, they thought, well, it would be really good to have this debug facility where we can request that the server tell us the last 400 requests. Well, that's really good for debugging, but it's also a really good amplification technique. So when you see that get list, it's actually identifies someone trying to use a reflection. If you happen to have NTP servers, please turn that off. It makes my job a lot easier. So it's got a very, Jeff mentioned it's got an amplification factor of about 500. And last year, it was the most popular DDoS attack. What we are seeing now is that that's dropping off in favor of the SSDP, and that is because the NTP servers are starting to shut down that hole. And so it's all about, cat and mouse. The DDoS attackers come up with something new. We close down that, they come up with the next thing. DNS, again, still very popular, simply because of the number of DNS resolvers that are out there. Again, strong signature, source port 53, large payload with a DNS response. Now, what works in our favor here, especially when we're building Route 53 defenses, is the set of DNS resolvers is very well known. And to their credit, they're also very well behaved. So by using a combination of heuristics around how those requests are made and the constrained IP space, we can very, very quickly get rid of reflection attacks because they tend to make DNS resolvers misbehave, and straight up DNS floods because they're not coming from the normal set of IP addresses. So that allows us to give exceptionally high protection to Route 53. And obviously, for your application, when you're configuring your own DNS resolver, there's only going to be a handful of them at most. And we'll talk a little bit later on about how you can use VPC and ACLs to make sure that any other DNS traffic coming in is simply not accepted. You're just simply reducing the surface area. There's others out there. RIP v1, if anybody has a really long memory, was that one of the original routing protocols of the internet? Believe it or not, there's still routers out there, and they do have this vulnerability that allows you to have an amplification attack. We saw one fairly recently, but luckily there are very, very few. Again, it has that well-known port, well-known payload, so we can take that out very, very quickly. Similarly, the fathers of the internet, or at least of Unix, decided that what we need is another debug tool called Chargen that will generate a stream of traffic. You just have to turn that off on your servers, and we'll make that one go away. So if you can help me out with that one too, that'd be really good. SNMP is a tricky one. SNMP isn't going to get turned off any time soon, but there's good ways we can deal with that too, although the amplification is quite large. Most SNMP agents are on network devices. They're deep in the network, so it's actually quite difficult for the attackers to find hosts or servers that they can take advantage of. Additionally, with SNMP v3, there's authentication, so that's not something we see very often, and typically the numbers aren't very high, so that's good. The common themes are, it's UDP-based, it's got a strong signature, it's not coming from where we expect, and the payload is unusual. And that combination makes these volumetric attacks very easy to identify and very easy to mitigate. Now, one of the other ways we can deal with volumetric attacks is by scaling up. The scary 200, 400 gigabit attacks that the media like are not the reality. The reality is down in the single-digit gigabits. A simple scaling architecture will deal with that. Using ELB with auto-scaling, EC2 instances behind them will actually mop up a lot of DDoS attacks without having to put in any other mitigations. If you couple this with Route 53, the story becomes even better. So the way this works is when a user is wanting to reach your ELB instance, maybe you've got an application and it's behind your ELB, and your users are making their DNS query to find out where you live. If it goes to Route 53, Route 53 is going to validate the state of your instances. Now, I want to point out, these instances are not EC2 instances per se. They're the actual component parts of the Elastic Load Balancer. And Route 53 is going to go around all the servers that make up that and validate their health. And that's great, because if everything's healthy, the user has got a selection of IP addresses that they can go and fetch the data from. Under a DDoS, or any other condition that might impact that server, it could be an outage, power outage, what have you, Route 53 is going to detect that. The instance is going to fail the health check. Route 53 is going to automatically take it out of the pool. So your users are only going to be directed to those healthy ELB instances. And that's really handy, because one of the things we do see is that DDoS attackers can be quite lazy. They grab all the IP addresses, they get an IP address, and they drill it. And they could be there for 15, 20 minutes until they notice that that instance or IP is actually no longer serving any kind of traffic. So we can take advantage of that, because you'd be surprised how much mitigations and actions you can take within that window. So this is quite a good technique. In our best practices, we talk about minimizing the surface area. The reason behind that is, for these volumetric attacks, if they can't find you, or they don't have a way in, or you're blocking the traffic, it's not going to impact. And the best ways of doing that are taking advantage of VPCs, which gives a couple of mechanisms: security groups and network ACLs. And they both work slightly differently. VPC is the default environment for your EC2 instances now. So if you're spinning up new EC2 instances, they automatically fall into a VPC. And the security groups on that VPC will deny everything. You then specify what traffic you want to allow in. NACLs are the other way around. NACLs, by default, let everything in. Then you can pick and choose what you want to stop. Very handy for like blacklisting. There's certain customers out there who know which attackers are coming after them. They know bad behaved clients, and you can use NACLs to stop that kind of behavior. So I want to walk through how you would set this up. And there's a couple other nuances here. So here's a very simple application. I've got my web app server, and it happens to have a SQL backend. That's where I'm fetching my data from. But what I'm going to do is I'm going to split out the various traffic. For my users, I've got my front-end ELB, and they're going to load balance across my web app servers. And I'm going to open up 80 and 443 to accept my HTTP and my HTTPS traffic. But I'm not going to forward it on the same ports. If I do a port mapping to 8080, even if the DDoS attacker comes after my web app, having discovered the IP, and there's various papers out there how one might do that, they're going to assume I'm serving on port 80 or 443. So if they try to attack my web app server directly, they're going to have no joy whatsoever. So that's a little bit of obfuscation. And then I can wrap those both in separate security groups, and I can tighten down my security group policy to make sure that they only accept traffic from where I expect. The next thing is my management. Now, simply best practice to separate out your management and your user data so that there's various scenarios whereby your user data might make it hard to get into your instance. If you've separated out your management traffic, that means you can always get in and manage your instance. And in this case, what it allows us to do is have separate security group policies for those two data streams. And then, of course, in and out is different. There may be valid reasons where we create outbound connections to download new software, provide upgrades, pull down new data. But typically, the places we're going to are not the places our users are coming from. So we want a different policy to deal with that. And here's a couple of examples. This is for the ELB. And the ELB basically says, I'll accept traffic from everywhere. That may not be the case for you. If you can tighten down that policy and say, well, actually, I only accept it from this set of clients, that's even better because you've reduced the amount of surface area. Similarly, we're only accepting from 18443, so any kind of random attack, if we think back to how the reflection attacks work, although they came from a source port 123 for NTP, they typically have a very, very wide range of destination ports. So we can take advantage of that as well and just make sure that only the ports that we need can be accessed. And then on the outbound, that's the destination of our web app server. On the web app server, we do something similar. We make sure that we only accept traffic from the Bastion host that's proxying our inbound management connection, or the ELB. That means no. So that's really handy to have that. And then the destination is obviously for the outbound NAT and then the MySQL. We can do something very similar with the NACLs. This is exactly the same sort of thing, but we have to turn it upside down, and we have to have that default deny rule. If we just put allow in, then by default, everything's allowed. So that default deny rule at the end is the one that stops anything other than what we've explicitly specified. So using those techniques, we can apply them and have applied them to our own AWS services. We have a very large number of edge locations, a very large number of regions, and we use the service and the scalability of the service by having multiple servers for our Route 53, multiple points of presence, multiple ingress paths to spread the attacks and also give us resiliency. We also have anycast, And we'll talk a little bit more in that in a moment. CloudFront, very, very similar. Obviously, a CDN, that's its main purpose. So it has all that capability of low latency by caching and doing minimal latency routing to the nearest edge location to serve traffic. But beyond that, as Jeff was saying, we have the capability to disperse an attack. So hypothetically, if you have a 100 gigabit attack, that's worrying. But if you take that 100 gig attack and spread it over 50 edge locations, it's only a 2 gig attack in those edge locations. So we can do traffic engineering to spread that traffic around. Additionally, because content is served as close to the request as possible, any localized DDoS attacks will have no impact in other areas. ELB, the term says it all, it's elastic. It load balances, it's auto scales. So by setting up your auto scaling, it's naturally going to scale up to any kind of incoming traffic, be it a flash crowd or a DDoS. It's all built in. And furthermore, as resiliency, you can specify that you want your ELB across multiple availability zones, giving your resilience not just to DDoS, but to any kind of failure condition in the network. As I mentioned, global presence, 11 regions, 53 edge locations spread throughout the world. Each of those edge locations and regions has multiple very large pipes out to the internet. People will ask us, okay, so you've got this really great infrastructure, you've got this really, you've got this good anycast, that's great. What happens if someone can affect the actual transit pipe itself? Fair question. Well, it's very unlikely that a DDoS attack can simultaneously affect more than one. I think the worst we've ever seen is maybe 2. So that means we always have the capability of serving the traffic. Multiple points of entry, multiple points of exit. As I mentioned, it's a CDN. It's only going to accept valid requests. Garbage traffic, garbage protocols, garbage requests, they're never going to make it back to your origin. Simply not going to see them or be charged for them. ELB handles TCP. Therefore, the same story applies. All that UDP traffic, all those volumetric attacks, they're never going to make it through an ELB. Route 53 has some additional capabilities built in there. When you use recursive DNS to find the IP address of your destination, Route 53 is going to give multiple ways of finding that information, and we'll talk about a little bit more detail in a moment. That means if something goes wrong with one of those authoritative servers, there's many other ways to find them out. And finally, as I mentioned, ELB spreads across availability zones, which is simply a good resiliency story. So let's talk about this, because I find this interesting. The first thing that happens when you make a DNS request is it trickles up through the recursive resolvers, is it has to find out who has the information. So Route 53 is going to give it multiple choices. And the way this works is we give 4 mechanisms or 4 CNAMEs that can be used to resolve this. 1 in each of these 4 top-level domains. 1 in co.uk, 1 in .net, 1 in .org, and 1 in .com. Sorry about that. And what that means is if there's any impact in there, then there's still always 3 more. Additionally, because we use anycast, if we have a failure in one server, someone else is going to pick it up. And then beneath that, we've got multiple servers serving that. We use a technique called shuffle sharding to make sure that no 2 customers share the same IP space. So that gives us additional protection and resiliency. And many edge locations where we can serve that request out of. State exhaustion. So this is the one that's kind of interesting from a different aspect. Security mechanisms and devices are there to stop the bad guys getting in. And that takes many forms, be it firewalls, be it IPSs, or DDoS-related devices. And one of the things on those devices you want to make sure of, if something happens to that device, you don't want to complete the attack. So if there's a failure in your device, you don't want to fail shut. So these devices typically have the capability to be configured to fail open. So if there's a device failure, goes into fail open mode, and your customer traffic isn't affected, which is ideal under normal circumstances. However, the DDoS attackers know this, and they want to take advantage of it. So a common attack technique is to launch one of these attack types, and it could be a SYN flood, it could be an IP frag, and what they're trying to do is overload your security device, make it fail, and go into fail open. Because once they've done that, your infrastructure is then vulnerable to exploitations, exfiltrations, login break-ins. So this is something that we're seeing more and more commonly. We'll see a DDoS attack, but underneath, what they're actually trying to do is break into your application, cross-site scripting, whatever it happens to be. And also, of course, the operators see this very large DDoS attack, and it tends to drag their attention. So something that we're very, very aware of. How does it work? So this is a SYN flood attack that we saw fairly recently. And as you can see, it's just repetitive SYN, 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 SYN. Appropriate for Las Vegas, I suppose. Now, what we've built into Wireshark here is we've actually annotated some of this and built in some additional metrics that we built in. And what this is telling us that we saw these large number of SYN attacks, and our hardware device returned a SYN cookie for them. SYN flood attacks are relatively simple to defeat with the right mechanisms. There's two really great techniques for defeating SYN flood attacks: SYN cookies and SYN proxies. And if you get it right, you can take them out. So let's look a little bit at how this works. So here we have a client, and that client is connecting to CloudFront. It doesn't have to be CloudFront. And we've got our DDoS mitigation system in there. And what that does is it uses a combination of SYN proxy, TCP proxy, and SYN cookies to handle the attack. Under normal circumstances, what's going to happen is a valid client is going to come with a SYN requesting the start of the TCP three-way handshake. We vend a SYN cookie. It goes back to the source. It gets turned around as an ACK, comes back. We validate the cookie, and we establish the connection to the back end. Of course, there's a little bit of downside to this. On the DDoS mitigation system, we have to handle two connections, the incoming and the outgoing. And we have to handle that cookie, which is encrypted. So there's a little bit of CPU burning there to handle these cookies. I'll talk about that in a minute. In the attack scenario, a SYN comes, and they're usually spoofed, because they're very easy to spoof. So we vend the SYN cookie, we pass it back, but because it's spoofed, there's never any response. But at this stage, we haven't wasted a connection, and the back-end server hadn't even seen it. So only valid connections are handled to the back-end server, which can then be optimized for its workload. For the DDoS mitigation system, or something performing this function, we have to optimize for two things. We have to optimize for a large connection table and a heavy CPU load to handle those cookies. And we do it on our DDoS mitigation system, but there's really nothing stopping you. If you can't use CloudFront or this particular technique, you could set this up with Nginx, put it onto one of the large compute machines, and blow out the connection table to do a very similar function. So although this is a technique that we use for protecting CloudFront, Route 53, and so on, it's something that you can set up for yourselves. Moving up the stack, the application layer. This is kind of tricky because application layer attacks are very carefully crafted. They require more work on the part of the attacker because they really want it to look like regular traffic. They're trying to make it as hard as possible to detect that. And HTTP is the obvious example, just repeated get floods. But it could be a DNS or it could be anything else that affects your particular application. This is one we saw against Route 53. It was a very, very large query flood of valid queries. There was nothing wrong with the queries. It spread across 34 of our edge locations, almost 60% of our fleet. It was in some of the largest attacks that have been seen. But the mechanisms that I talked about earlier, knowing what our traffic looks like, knowing what the sources are, allows us to see exactly what that traffic looks like. We know how many queries and we know what types of queries we typically get. And we can identify that using heuristics of how that little difference between what our regular traffic and this attack is to take advantage of the priority queuing and drop that traffic. Net effect was that there was no impact on the Route 53 response time during the course of this attack, and eventually the attacker gave up. It's interesting that we're actually seeing fewer and fewer Route 53 attacks now. I'm not quite sure whether that's because they're changing tactics or whether they just get bored. So when you're thinking about that, you want to look at where the vulnerable parts of your architecture are. And this is something we look very carefully at. There's facilities that you can use to protect, add additional layers of protection. Geo-restriction is something that's available on CloudFront, but it's something that you can equally do with carefully crafted security groups. Slow lotus is a well-known attack type. We take care of that in CloudFront, but Nginx has mod plugins that will equally do the same job. And of course, you may have heard yesterday, we announced a WAF as part of CloudFront offering now, so that's something you can take advantage of. Again, the same capabilities are available in the Amazon Marketplace. There's a wide variety of commercial WAF solutions that have this capability as well, so if CloudFront isn't something that suits your application, there are many other solutions. If you want to do the work yourself, you can take advantage of things like Nginx and Lua. So there's many solutions out there that will help solve this problem. And this would be a way that you could build up an architecture using the best practices. I've got a web server. The DDoS attack comes, so the first thing I'm going to do is scale up my back-end instances to handle the load. I can put in ELBs and WAFs, and I can take CloudFront and put it in front, taking advantage of our dedicated mitigation hardware. And the key takeaway there is we want to put in multiple layers. There's no one solution to all the DDoS attacks, be the volumetric, the stateful, the application layer. And I guarantee that as quickly as we plug those holes, the attackers are wanting to come up with something new. They're poking at what's the next protocol we can take advantage of. It's very lucrative for them. We want to make sure it's not lucrative for them. So I've done all that, right? We've set up our architecture. I'm doing best practices. I've got my mitigations. You want to talk about what happens if under attack. I've seen an attack coming. I've got my customer. This isn't what I expected. How do I take care of it? And I'm going to hand this back to Jeff because Jeff runs the team that takes care of this kind of thing.
Thank you. So customers frequently ask us, okay, that's great, but what do I do when I'm actually under attack? Like many things, preparation is key. If we can address DDoS attacks before they occur, then as a customer, you can be better prepared for the attack and for protecting your availability. One resource which is tremendously valuable is your account team, specifically the solutions architect. A solutions architect can understand your specific use case and help you build a DDoS resilient architecture in order to protect your availability by mitigating DDoS attacks. We also provide some self-service tools to allow you to do this yourself. In the AWS Security Center, we provide a white paper called AWS Best Practices for DDoS Resiliency. It includes many of the reference architectures and best practices that Andrew just discussed. We also have the AWS Security blog. Recently, we made a post discussing VPC and reducing attack surface. That post has a lot of the reference security groups reference NACLs in order to allow you to implement this yourself. It's essentially a step-by-step guide. Beyond that, what happens when you're actually under attack, preparation has failed, and you still need support? For this, we recommend AWS Support, specifically business or enterprise tier. The business tier is tremendously useful because it includes support by phone, chat, or email. It's also a great value. If you require the fastest possible response time, you can opt for enterprise support. And this is also going to provide you with a dedicated technical account manager, or TAM. The TAM not only understands your business, understands your use case, but can help drive rapid resolution of cases where you're under attack or any other issue that you're having with your application. Information that you're going to want to provide us, frankly, as much information as you have about that attack. The instances, the IP addresses, the load balancers, CloudFront distributions, Route 53. Whatever it is that you know is being targeted, let us know so that we can drive a faster resolution. Let us know what regions are being targeted or where these resources exist in AWS regions. Let us know when the attack started, the different vectors. Are you already aware of what type of traffic it is? And can you help us contrast that against your known good traffic? Also, let us know if you know the specific source of the attack. Maybe you have a list of IP addresses that are contributing to the attack. These are things that we can find out with tools that we've built, but if you already have this information, it allows us to act much more quickly. And lastly, intel, or intelligence. Let us know anything you know about the attack or the attacker. Maybe you've received a threat, or you know who the perpetrator of this attack is, and that helps us understand some things like, if we've seen this type of attack or we've seen this threat before in the past, we might already have a clear idea of the signature and what type of volumes they're capable of. So for this information and other information about security on AWS, features, guidance, and our compliance initiatives, you can check the AWS Security Center at aws.amazon.com/security. And that concludes our presentation. I'd like to thank you for coming. If you haven't already downloaded the app, please do so. Please submit an evaluation that's very useful to us. And don't forget to check out Nate Dye's presentation on AWS WAF this Friday at 9 a.m.